Integration is mathematically working backward to recover lost information. To see how this works, look at this equation. F of x equals x squared plus 5. When you take the derivative, you are measuring the rate of change. Because the number 5 is a flat constant, it does not change. Taking the derivative destroys it entirely, leaving us with just 2x. If we want to reverse that operation and integrate 2x, we hit a wall. The derivative wiped out the original constant, and we have no way of knowing if it was a 5, a 10, or a -7. To account for that destroyed evidence, we write plus c. This gives us the indefinite integral, the complete family of all possible original functions. From here, you can rely on a standard table of baseline rules to handle simple powers, sines, and cosines. You can also apply linearity rules to split sums apart and pull constant multipliers out to the front of the integral to keep your algebra clean. Knowing these baseline rules is the first step. The real challenge of integration occurs when you face compound functions, where the original structure is buried deep inside the algebra. When dealing with composite functions, functions nested inside other functions, the baseline rules fail. We must reverse engineer the chain rule by looking for an inside function, whose derivative is sitting right next to it on the outside. Take a look at this integral. We have a complex expression inside the cube root, 1 plus x squared. Outside of the root, sitting by itself, is an x. We can extract that inner function and define it as a new variable, y. If y equals 1 plus x squared, its derivative is 2x. Notice how close 2x is to the isolated x in our original problem. Now we hit the mechanical step, where errors frequently happen. We must rearrange this derivative equation to solve specifically for dx. Multiplying both sides by dx and dividing by 2x yields a new equation. Dx equals 1 over 2x dy. Now we substitute everything back into our integral. We replace the inside function with y and the dx with our new dy expression. Because we selected our inner function correctly, the x on the outside cleanly cancels with the x in the denominator. All the x variables are gone. Substitution operates as a translation exercise, converting a complicated problem into a simpler language where the standard baseline rules can finally be applied. Sometimes substitution fails because you have two completely unrelated functions multiplied together. When that happens, we reverse the product rule using this formula, integration by parts. This formula forces us to make a choice. We must pick one piece of the function to differentiate and one piece to integrate. Look at the integral of x times e to the x. If you assign the pieces incorrectly, you will create a much worse integral. On this first path, let's set g of x as e to the x and f prime of x as x. When we run those through the formula, the new integral we have to solve becomes 1/2 x squared times e to the x. The exponent increased, making it structurally harder to solve than the original problem. Now look at the second path. If we reverse our choice, setting g of x to x and f prime of x to e to the x, the derivative turns the x into a 1. The resulting integral simplifies down to just e to the x, which we can solve immediately. To eliminate the guesswork, you can rely on an objective hierarchy called LIATE: logarithmic, inverse trig, algebraic, trigonometric, and exponential. Whatever term appears highest on this list is the term you should choose to differentiate. Let's test that hierarchy. Here is a slightly more complex problem, the integral of x squared times e to the x. Pause the video and use LIATE to decide which term to differentiate. Resuming, x squared is algebraic, so it sits higher on the list than the exponential e to the x. Differentiating x squared gives us this result. Notice that the new integral still has an x multiplied by e to the x. Reversing the product rule operates as a loop. You often have to apply the technique multiple times, chipping away at the algebraic power until you finally reduce it to a baseline rule. Even with flawless algebra, your result is valid only if the function exists on the exact interval you are analyzing. This graph of 1 over x shows a sharp vertical asymptote at x equals 0. Integrating blindly across a gap like this will output mathematically false data. To prevent errors, you can organize your approach into a mental flowchart. First, check for a basic rule. Next, apply linearity to split up the problem. If it is a composite function, use substitution and carefully solve for dx. If it is a product of different functions, use integration by parts guided by LIATE. And finally, the crucial step that is forgotten most often, always add plus c to account for the destroyed constants. Mastery of the indefinite integral comes from systematically dismantling the layers of differentiation to reveal the original function hidden within the algebra.